So YouTube is live now, and that's kind of important because it seems some of the vid students got sick yesterday.
Yeah,
You
yeah,
heard
I
that?
heard about that.
Yeah.
Yeah.
So I think we'll probably be watching over this. At least I'll send him the link just now.
Sure, sure, sure.
Is this the?
And the screen is shared.
Yeah, I will,
Okay,
I will
okay, good.
share the screen. Well, I will share. Yeah, I mean, probably that they'll probably be seeing this screen, but I can even not. So let me just check here.
Sure.
You would like? Okay, let's see. Presentation. Is this the one?
This is the one.
Okay, so you can just move around
Okay, with
the
the
keys, and I think
keys.
it's showing up there. We just need to turn off the lights a little bit. Okay, and if you maybe, yeah, sometimes if you want to write something here, you can turn on the spotlights.
Okay.
If you're gonna
Okay,
maybe
okay.
for a bit longer, maybe it's like easier to see
Yeah.
what's happening. And otherwise, I think we're ready on this side. Yeah, and I will just send in the link now.
Sure.
We just have to maybe click Zoom. Oh, yeah, easy. So maybe one more minute. Yes. All right, welcome everybody to the second day of the 12th Joburg School in String Theory, and today we're pleased to have, very pleased to have Mario Agenda from Turin, who is going to present a very extensive and starting from an introductory lecture today, lecture series on supergravity and gauge supergravity. So Mario, looking forward to your lecture.
Okay. Thank you very much for inviting me here, and it's very nice to be here. It's the first time for me to be in this beautiful country. So let's talk about my lectures. The aim of this lecture. Let's talk about my lectures. The aim of these lectures is to give an introduction to supergravity, a general introduction to supergravity, its mathematical formulation, in particular to gauge supergravity. Okay, I would like to give you a kind of taste of what are the mathematical structures occurring in these theories. I thought it better to give a preliminary slide presentation, okay, because I thought that maybe not everybody in the audience is familiar with the exterior form formulation of general relativity, field bind formulation, and all these things. Okay, so I thought it better to give a preliminary presentation on a slide presentation, and in which I set the stage, okay, for the subsequent lectures. And I fix also the subsequent lectures. And I fix also the formalism, okay, the notation and everything. So let me give first an outline of this talk. I'll give here of these lectures. Outline. So I will give this, let's put 0, preliminary presentation. Then I will discuss, give a introduction and motivation, general motivation. 2, I will deal with review the general features of engaged supergravity. Engaged supergravity. Supergravities. Duality. Structure of these theories, but by duality structure I mean global symmetries. Global symmetry is a peculiar feature of these engaged supergravities and makes them particularly appealing, okay, as theories. And then I will move to gauge supergravities. Gauge supergravities, okay, and I think it's going to be tomorrow. Okay, we're going to start dealing with gauge supergravities tomorrow. So the general formulation. Okay, so the general ideas behind gauge supergravities, and what should it look like here? Formulation of the gauging procedure. Six, duality covariant formulation. Covariant. Of gauge sutras and the embedding them. Then I will touch upon the topic of tensor hierarchies, which follows from this formulation, naturally follows from this formulation. A, gauge maximal supergravity. We talk about gauge maximal supergravity. If I have time, I will discuss in detail some examples of dimensional reduction, okay, which generalize the ordinary well, the trigger dimensional reduction on a torus because it contains some fluxes or some non-trivial internal geometric structure of the manifold, like the Church-Schwartz compactification. I will review, if I have time, okay, and show how them lead to a gauge supergravity in lower dimensions. So, examples of dimensional reductions with fluxes. So here we will see how gauging, that is the existence of an internal low symmetry, follows from dimensional reduction in the presence of fluxes. Okay. Okay. So this is roughly speaking the outline of the course. Let's start from the preliminaries. Okay. So let's start with some references. These are the main references on the general subject of supersymmetry and supergravity. They're very well-known references. Okay. While for the specific, while for the specific subject of gauge supergravities or dualities in gauge supergravities, so for the specific subject which will be dealt with in this course, okay, I can suggest these references. Okay, the first is the lecture notes, which should be available. Which should be available to you on the website, and then these are recent reviews on the subject. Okay. Please, if you have any questions, don't hesitate to stop me and ask. So let's define what we are talking about. So what is supergravity? Notion of what supersymmetry and supergravity is. Notion of what supersymmetry and supergravity is. So supergravity is a field theory which is invariant under local, that is space-time dependent, supersymmetry transformations. Okay. Now I think I have little to add to what Sam said yesterday as an introduction to supersymmetry. It was a very nice introduction. So I just had very few things. I just recall that supersymmetry is a symmetry between bosons and fermions. It relates bosons and fermions acting on a bosonic state gives you a fermionic state, and acting on a fermionic state gives you a bosonic state. And therefore, it associates with each particle, a superpartner with a different spin statistics. Now, in order to do so, then of course I also assume that many of you are familiar with the main motivations behind supersymmetry. It's known that supersymmetry has the beneficial effect on a field theory of improving its ultraviolet behavior, because it makes ultraviolet divergences less severe. This is due to the fact that the contributions to loop divergences coming from bosons, bosonic and fermionic field, partially cancel. Okay, so there's this beneficial effect, and this is the reason why supersymmetry was put forward as a possible solution to, for instance, the hierarchy problem in particle physics. Hierarchy problem related to large ratio between the Planck scale and the standard model scale. Okay, specifically it protects the mass of the Higgs boson from dangerous quadratic ultraviolet divergences, one loop divergences. You all know, it also makes the renormalized coupling constant of the standard model. This in the minimal supersymmetric extension of the standard model converge. It extrapolated through their renormalization loop flow, converge at a very high energy. Okay, at an energy scale of about 10 to the 16 GeV. It also provides a viable candidate for dark matter, very light particle. So, in order to connect two states with different spin statistics, the generator of supersymmetry transformations, which we denote by Q, should belong to the spin 1/2 representation of the Lorentz group, which we denote by SL2C. In particular, it should belong to this representation 1/2 0 plus 0 1/2, which is the representation of spin 1/2 particles, as you know. So, what are the index structure, or what is the index structure of these supersymmetry generators? So, supersymmetry generators are fermionic generators, in that they carry an index alpha in this four-dimensional representation, running from 1 to 4. This is the spinorial Majorana representation of the Lorentz group. Then we can have different amounts of supersymmetry at any dimensions. Here we are working in 4 dimensions, okay? And the number of supersymmetries is labeled by this capital index A, okay, running from 1 to n. N is the number of supersymmetries. And this index A is acted on by a compact group, which is the automorphism group of the superalgebra. It's called R-symmetry group. For the Poincaré superalgebra, that is the supersymmetric extension of the Poincaré group, this group is UN for any n up to 8, and SU8 for n equal 8. Okay? So, according to this index structure, also the parameters, okay, have the same. According to this index structure, also the parameters, okay, have the same index structure, okay, and they are Grassmann numbers. So they are anti-commuting numbers. Now, consistency of the definition in a relativistic field theory of these generators imply that they should satisfy commutation relations instead of anti-commutation relations. And in particular, in the super Poincaré algebra, which is the one which superparity is based on, okay, the anti-commutator of two supersymmetry generator closes on space-time translations. Space-time, the generator of space-time translations is denoted here by P nu. Is one translations is denoted here by P nu. Is one of the generators of the Poincaré group. Okay. Now, an interesting from this anti-commutation relation follows that the commutator of two supersymmetry transformation on any field amounts to a space-time diffeomorphism, that is a space-time translation. You can see this from by inspection of the effect of a supersymmetry transformation on a bosonic or a fermionic field. The general form of the supersymmetry transformation of a bosonic field is this one here, written here. Here I will denote it by B, generically any bosonic field, by F, generically any fermionic field. So the variation, supersymmetry variation of a bosonic field, this is written very schematically, can be written as epsilon bar times a fermionic field. Okay, this result is a bosonic field. Okay, all spinorial indices here are contracted. Okay, and they are understood. Okay, they are suppressed. And the variation, specific variation of a fermionic field has this general form here. Okay, and the result is a fermion. Okay, and they are all proportional to the supersymmetry parameter epsilon. As we will see, there's going to be another fermion in supergravity theories, which is the gravitino. And for gravitino fields, the variation, supersymmetry variation, has another term, which is the gauge variation, transformation of the gravitino. It's a derivative of epsilon. Okay, but for the time being, let us consider these general expressions, and you can easily verify that if you do perform a commutator of two infinitesimal supersymmetry variation on a bosonic field, what you end up with, this is an easy exercise, you just perform two consecutive supersymmetry transformations of it, you end up with a infinitesimal spacetime translation, defined by a parameter psi, which is a bilinear of the two supersymmetry parameters. Okay? So, from this it follows that invariance and local supersymmetry transformations, namely invariance under supersymmetry transformations parameterized by epsilon parameters depending on space-time, okay, implies also invariance under local space-time translations. But local space-time translations are general coordinate transformations, are diffeomorphisms, okay? And invariance under diffeomorphism is the symmetry principle underneath general relativity, okay? So this implies that a theory which is locally invariant under supersymmetry transformations must contain Einstein's theory of relativity. Now, from this heuristic argument, of course, it doesn't follow. This is just telling you that it is necessary for a locally supersymmetric theory to contain Einstein's theory of relativity. Constructing it, you know, proving that it exists and constructing it is highly unusual. Indeed, the very fact that Einstein's theory of relativity admits a supersymmetric extension is a non-trivial result. It was proven and it was constructed by Ferrara, Friedman, and Liebenhausen in 1976. Okay, in 1976. Okay, using the second order formalism for the spin connection. And then it was derived a bit later, the same year, by Desel and Zumino, but using the first order formalism for the connection, the spin connection. I will define what these formulas are in a moment. Okay. So the main ingredient in a locally supersymmetric theories, which are called supergravity because they contain Einstein's gravity. They are a supersymmetric extension of Einstein's gravity, so they are called supergravity. So the main ingredient, new ingredient with respect to global supersymmetric theories is the gravitino field. The gravitino field is the gauge field associated with this new local invariance, this local supersymmetry invariance. Okay, so what are the quantum numbers of this field? We know, as for any gauge fields, okay, its indices. It should carry the indices of a generic parameter of the local symmetry, and in addition, it should also have a space-time index because it's a connection is a one form. Okay, so it's from a space-time point of view, it has this vector index, okay, mu. So since the generic supersymmetry generator has an index structure alpha A, okay, the gravitino field should have the same index structure alpha A, and in addition should have this index mu. Now, so in discussing describing supergravity, okay, we are forced to describe Fermi fields on a curved background. Sure.
I didn't understand why there should be an additional space-time index.
Yes, because you see, in ordinary gauge theories, although this is not properly a gauge theory of supersymmetry, but in ordinary gauge theory, what you do is you associate. Let me write it here. You introduce, to make the theory local, you introduce a gauge field. Okay, now this gauge field. So you introduce a connection, basically. Okay, this connection is a one form. The idea is that using this connection, you construct covariant derivatives. So it has to have a space-time index because doing a connection, it has to combine with ordinary derivatives so as to make a covariant derivative. Okay. Now, For supersymmetry, as we shall see, things are a bit more complicated, but the general idea is this one. As we see also, even local invariants under but the general idea is this one. And as we see also, even local invariants under local space-time transformations, translations, diffeomorphisms, okay, can be associated with a gauge field of this form. Okay, not of this form, but according to the same rule. And this gauge field is the graviton. So it has the same index structure as the generator of space-time translation. Okay, and in addition, it has a space-time index. This is going to be the field line field, which I'm going to introduce in the next slide. Okay, so the general rule is this one. Okay? For gauge theories, this is normal. Okay, because you associate with these local invariants a connection, and that connection has a space-time index. Okay. Okay. So since we need to describe fermions in supergravity theory on the curved spacetime, okay, then we have to formulate Einstein's theory, so gravitational theory, general relativity, in terms of field binding, for the reason I'm going to outline here. So just as general relativity, supergravity is defined on a pseudo-Riemannian spacetime manifold with a Lorentzian signature endowed with an affine matrix, okay, which is a matrix connection, which I denote by gamma, okay, capital Gamma. Now, the presence of fermions, as I just said, like the gravitational field, calls for the so-called tetrad or vierbein in 4 dimensions, or in generic dimensions, field line description of the matrix. Why do we need this kind of description for this kind of formulation for describing fermions in curved spacetime? Well, in flat spacetime, fermions are described as fields transforming in a specific representation, the fermionic representation, a spinorial representation of the Lorentz group, or better, of a double cover of the Lorentz group, okay, the spin group. And in flat spacetime, in Minkowski spacetime, the Lorentz group is an isometric group, so it's manifest. It's axion coordinates, coordinate differentials. So it's an isometry, it's a symmetry of spacetime. In a generic curved spacetime, we lose this symmetry because a generic curved spacetime may have no symmetry at all. So where is the Lorentz group that we need to define spinorial fields? How do we define this Lorentz group? The answer to this is by making reference to the local inertial frame. Okay, so by describing the matrix through the field line, through so-called field line fields. So it consists in writing at any point the matrix, which is a 4x4 matrix field. So in this way, using these matrices P mu A, okay, depending on X. Eta AB is the flat Lorentz matrix. Okay, simply the diagonal matrix, plus, minus, minus, minus. Okay, so that we can do this is guaranteed by general properties of matrix theory, that we can always do this. But what is the meaning, the physical meaning of these objects, in particular of these indices A and B? The indices A and B are called rigid indices, as opposed to mu, which are curved indices. Rigid indices, they are associated with the so-called local inertial frame or free-falling frame, the Einstein lift, okay, that we can define at each point in space-time. The local inertial frame is defined by a set of coordinates labeled by A or B, okay, a set of coordinates which have the property that in these coordinates, the matrix at a specific point, just at that point, is equal to eta A. So you can choose basically a basis of the tangent space, okay, which is called the tetrad basis, on which the matrix is just A. But this you can do at a single point, at a specific point, at any point, okay, but not in a neighborhood of that point, just at that single point, okay, you can do that. And moreover, in this coordinate system defining the local inertial frame, also the first order derivatives of the matrix vanish. But in general, the second order derivatives will not vanish if the manifold is curved at that point. Otherwise, you will have a flat matrix at that point. Okay, but in general, the curvature is maybe non-vanishing in a single point. Okay, so you can make the matrix coincide with eta at that point. You can make its first order derivative vanish at that point, but not the second order ones in general. Okay, so this coordinate frame defines the local inertial frame, the free falling frame, where local inertial frame is very important in general relativity because it defines the relationship between general relativity and special relativity. So it allows you to define the limit within general relativity where to recover special relativity. And this you can define at each point in space-time. Okay? So, V, what's the relation between these V matrices and, oh please.
This is why the manifold is
Yeah, the manifold. Look, it would be Euclidean, precisely. So the reason why you can make the matrix choose a coordinate frame which is as that form there with that signature is because we are a pseudo-Riemannian. Okay, if we were Riemannian, then you could do the same thing, but with a delta instead of eta. So plus, 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 plus. Okay. So you could not change. You cannot really change the signature. That's something you cannot do. Okay.
So I see the vision was the minus signature.
I apologize for that.
For the whole lecture.
For the whole lecture, it's going to be like that. I really apologize for that. But I know that there are different communities, and yeah. So please forgive me. Yeah, I'm going to use it. You also use it. Yeah. For the courses, yeah. GR usually, yeah, because it somehow, in some sense, it is more natural to use the mostly class because you get to Euclidean, ordinary Euclidean, when you restrict to space. Okay, so what is the relationship between this V, which are called the Wilbine field, okay, and the local inertial frame? Well, these V are nothing but the Jacobian of the relating the coordinates of the local inertial frame to the generic coordinate x mu at a point. At a point. In general, in the open neighborhood of that point, V are not the Jacobian of anything. Otherwise, you would have a flat matrix. Okay, so that's good. Good. So you can describe this. You can describe these matrices V mu A in terms of one force. You define one force. At any point, which are V mu x, V mu A x, mu or x, whatever, suppress the index of x, dx mu. Okay, these are one form fields. Okay. Good. Sometimes in textbooks, they of course these belong to T star x of x. That is to the. You know this notation? This is the okay. But sometimes people use the corresponding dual basis in the tangent space of X. Okay, the relationship between the two is dA E D is equal to delta E. Okay, so this means that E A is just dA mu D over dx, where dA mu is just the inverse of dA. This is what people call the deltas, the delta frame. Okay. Good. So, of course, the locally measured frame is defined modulo Lorentz transformations, which act on the rigid indices. Now, these Lorentz transformations, by definition, are associated with each point in space-time. And in order to see that, you have to use the tether description of the matrix. Okay, that makes local Lorentz transformations manifest. Okay, so you see, if you transform the field line by acting on the rigid index by any Lorentz transformation, okay, then you have an equivalent description. Yes.
Is that the full of 1 kind of 3, or is that the full of 1 kind of 3, or is this just
The full?
the old 1 kind of 3 you got there, the full? Or the description match good?
No, it's the full one. It's the full one. Yeah, in general, you see, what you can act by the full, so 013, so 013, and then this is left invariant. So the description is left invariant. Okay? So anything should be invariant under such Lorentz transformations. So all quantities in general relativity should be invariant under this local Lorentz transformation, which is a local Lorentz, which is a Lorentz that you associate, I repeat, with each point in space-time. Okay? And this is a true gauge symmetry. This is the only true gauge symmetry of general relativity. So by gauge symmetry, I mean that in mathematical language, it's a truly vertical group. Okay, while space-time diffeomorphism are not true gauge transformations. The reason is that the parameters of local space-time diffeomorphisms are space-time coordinates. Okay. And the dependence of the fields on space-time coordinates cannot be, a gauge, the effect of a gauge transformation, because gauge transformations do not alter physics, while in the dependence of a field on space-time coordinates, there is dynamics, there is physics. Okay, so space-time coordinates are not gauge coordinates, cannot be. So that's why local space-time translations are not properly gauge transformations. They are local invariances, but they should not be regarded as proper gauge transformations. These are proper gauge transformations. Okay, nothing should. The dependence on the parameters of this group, okay, is totally unphysical. It's totally unphysical. Okay, now how are spinor fields defined on spacetime? Spinor fields are fields defined on spacetime. Spinor fields are fields which transform in a spinorial representation of spin 1,3, which is a double cover of SO13 at any point in time. So, in general, spinor fields transform under the symmetry group of the point. This is a general feature. Spinor fields transform under the symmetry group of the point, and SO13X is a symmetry group of the point. Is related to the choice of this basis, of this theta basis, on the freedom we have to choose this theta basis, this field line basis. Okay, and nothing should depend on this. Okay, when we're going to deal with supergravity, we'll see that besides this space-time manifold, there's going to be another manifold spanned by the scalar fields. So on top of it, there is another internal manifold. The rule is always the same. The fermionic field should transform under the local symmetries of space-time, local Lorentz, and of this new manifold. but the rule is always the same. Spinors always transform under the symmetries of the point. Okay, so let us recall what the local symmetries of our theory, supergravity theory, are. So we have invariance on the local supersymmetry transformations. The generators are Q alpha A, and they correspond to the gravitino fields, okay, psi mu alpha A. I will often suppress the index alpha, okay, when writing values formula. What is the spin of the gravitino fields? Let us write the gravitino fields, by turning the curved index mu into a local Lorentz index. This I can do. Define a field like this using the field bind. Using the field bind, at any point I can turn alt mu into a local Lorentz index, which is a rigid index, which is associated with a well-defined representation of the Lorentz field. So one's already on. Okay. Now we can assess what the representation of this field is with respect to the local Lorentz group, because this is an index of the local Lorentz group. This is an index of the local Lorentz group. Okay, this is another index. We are not going to talk about that. Okay, so this is a spin one index times a spin 1/2 index, which is this one. Okay, so if you do the product of a spin 1 times spin 1/2, you get a spin 3/2 plus a spin 1/2. Okay. Now, elementary particles are in irreducible representations of the Poincaré group. Okay, and the representation of the gravitino field is 3/2. We can get rid of this spin 1/2 component by imposing the following condition: gamma A psi A, gamma A psi A equals to 0. This object here transforms in the spin 1/2 component. This contraction selects the spin 1/2 component of the gravitino field. And by setting it to 0, we are really selecting the representation of the gravitino field. Okay? So when we quantize the gravitino field, we need to impose this condition here, because we need to select the truly propagating degrees of freedom, which are the spin 3/2. Right? So the gravitino field has a spin 3/2. Then we have space-time invariance under local space-time translations. You see here what I was telling you before. The generators of space-time translations are PA, okay, and we can associate with them the field bind field, which has two indexes: this index of PA, so the same index as the generator of the local symmetry, plus the space-time and additional space-time index, according to the same rule. Okay, so gauge fields have this general index structure. Okay, the core of the infinitesimal generator plus the space-time index. Okay, and this describes the graviton spin 2 field, the graviton field. So the field by field describes in general relativity or supergravity the graviton field, and it has a spin 2. Then we have invariance under local Lorentz transformations, and the generators are denoted by JAB. These are true gauge transformations, as I said, and the corresponding gauge fields are nothing but the spin connection. And you see they have the same index structure as JAB, okay, but an additional space-time index, because you have to construct using them connections. So covariant derivatives. Derivatives which are covariant with respect to the local Lorentz transformation. This is a true Lorentz gauge transformation. Okay. Are you familiar with the spin connections? Do you know how they are defined? Let's define them.
sorry, Professor. Just as a reminder, the indices A, normal script A and B's, those are the ones we saw in the big.
On the field, right? These are the space, rigid space-time indices. These are the indices labeling the local inertial frame. Yeah. So they are defined modulo local Lorentz transformations. So local Lorentz transformation act on AB. They don't act on U.
So one more thing about these indices is that before imposing the supersymmetry, like for example, in variance under local supersymmetry, our alpha index is downstairs and A is upstairs. And after it, same. But when we do invariance under local space time translations, then the digit index goes upstairs. And same.
Yes. The position of the A index.
Yeah,
That's not relevant because you see, why the position of alpha, that's important. The position of the A and B indices is not really important because you can raise them or lower them using eta AB. So using the Lorentz, the flat Lorentz metric. So the position of A, B is not really important. You can define the position of the mu index is important. Okay, that you can change by contracting with the matrix, space-time matrix, G mu or its inverse. But as for the rigid space-time index, well, this is nothing but eta A B dB. Okay, so just changing the space components by the sign. Okay. So how is the speed connection defined? So we have defined on our manifold a matrix affine connection. So we have a matrix affine connection. Matrix affine connection. Let us denote by gamma the connection symbol. Okay, this allows us to define covariant derivatives. Okay, so and we have our symbol, and we have our field line, local field line. Okay, now we can apply the covariant derivative defined in terms of gamma to be mu A. That we can do. Okay, how is this defined? Well, this is d mu A minus mu rho d rho A. Okay, this is the definition. Now I call this minus omega A B mu V mu. So I call this action this. So I define omega through this action. The effect, the result of this action here, okay, I write it in this way. And this defines our spin connection.
Is there a comma there after B?
After B, yes, there is a vertical line just to distinguish between these two indices. Okay, otherwise they tend to mix. Okay, so this is the main function. This is our spin connection. Okay, and you see it's contracted with V. Okay, through its rigid index, the second rigid index. Okay, so X on the second rigid index, so that we can define a big covariant derivative. Okay, mu of VA mu, which is plus omega A mu V mu. We define this like this. This is a definition. Okay, if we define the covariant derivative like this, then we see that this is zero. But it's zero because I define omega like this, so it's trivial. But this is the so-called first field by postulate. Okay, first field binding postulate. So the covariant derivative of the field binding, okay, covariant with respect to space-time translation and the local Lorentz transformations, okay, is 0. Okay. Now omega is the connection associated with local Lorentz transformations because it has to, you see, if I perform a local Lorentz transformation with parameters which depend on space-time, because local Lorentz transformations do depend on space-time, they are defined at each point in space-time, then this is covariant provided omega transforms correspondingly as a connection. Okay, so omega is the connection which makes this derivative covariant also with respect to local Lorentz transformations. And I suggest you to do this as an exercise. Work out the transformation properties of omega so that D, defined like this, is invariant under local Lorentz transformations. Right here. Exercise. Determine transformation properties of omega under local Lorentz transformations lambda AB X in SO or O13. Okay?
And there is a very basic question. So we are defining, like we are saying that omega is a connection on the locally flat metric, right?
Yeah.
But isn't the connection on locally flat metric 0?
No. It's a connection not. It's not associated with it. It's a metric connection. That is, it leaves the metric, the flat metric invariant. So this, the fact that omega is a metric connection means that this connection leaves eta AB invariant. Okay, basically it has to be invariant. Okay, but omega is not the connection associated with this metric. Okay, omega is the connection associated with local Lorentz transformations. So it cannot be defined in terms of eta as you would define gamma as a Levi-Civita. Okay, omega AB seen as a one form. Okay, is in the Lorentz, is in the local Lorentz group because of this condition here. So this means that if I act on this by eta, okay, this must leave eta invariant. The action of omega must leave eta invariant. Okay, this is what you get from here. But this is amount to saying that this is equal to minus omega CD eta dA. Okay, omega AB belongs to the algebra SO1, the Lorentz algebra. It acting on eta leaves it invariant. Okay, it follows from here, from this one. Eta has to be invariant, okay, constant. So, okay. So this is the exercise, the useful exercise. Okay, you will see that delta omega prime should be lambda minus 1 omega lambda plus lambda d lambda. I suppress all indices. Okay, lambda minus 1 d lambda. So it has to transform as a connection, and you have to verify this. Okay. So the second two are manifest in supergravity. Two are manifest in supergravity and general relativity in general. The first two are manifest simply by defining an appropriate covariant derivatives. Covariant derivative which contains the affine connection, metric affine connection gamma, okay, which is torsionless. So we take the Levitine symbol, okay, omega, and the torsion is in omega. All torsion is in omega, plus possibly other terms associated with local invariances, which we are going to introduce in the next lectures. Okay, we are going to introduce, for instance, here. Oh, what happened? I have to press. Yeah. Okay. Okay. Fine. Thanks. So we are going to introduce local Lorentz invariances. Not local Lorentz. Local internal invariances. Okay, gauged by the vector fields, and then we will need to add an extra connection. This time depending on the vector fields. This is implied by the gauging procedure, but we are going to discuss about this later. Okay, so far this is the structure of the covariant derivative that we will use. All torsion is in omega. As we are going to see in superiority theories, there's going to be torsion. Okay, so the gravitino field. Let's spend a few words about the gravitino field and its description, dynamical description. So the gravitino is a massless spin-free half field, as we said. Its dynamics is described by the so-called Rita-Schwinger equation, which is an equation that was found by Rita and Schwinger in 1941, so a long time ago, and it has this form here in flat space-time. Okay, so it's a kind of generalization of the Dirac equation, but for spin-free half. Spin-free half fields. Okay, gamma mu are the usual defined usual Clifford algebra, and you see that this equation has this invariance, has this local invariance. So it's invariant if we transform sin mu by the addition of a derivative of some spin 1/2 field. Okay, so local spin 1/2 parameter. So this is a local symmetry associated with the spin 1/2 parameter. This is a supersymmetry. Okay, you see flat space time. There's no problem, because if you vary sign this way, okay, you have two partial derivatives which are whose indices are anti-symmetrized, so it's zero. And this is what you need, in fact, to define a massless spin-free half field. As for all massless fields, you need to decouple the longitudinal modes, which are ghost modes. They are unphysical. So you need to decouple, just as for the spin 1 electromagnetic field, A mu. Okay, and this is guaranteed by the gauge invariance. Okay, so this unphysical component you can dispose of by gauge fix. It's just unphysical. It just does not enter, does not have any physical implication, and you can just gauge fix it. The same is true for the gravitino field. The gravitino field is a massless spin-free half field, okay? And let's not update it now. Okay. And so it has an unphysical longitudinal component, which is described by a spin 1/2 field, okay? And this is telling us that this spin 1/2 field is unphysical, so it will not enter the dynamics. Okay.
Professor, so there's a floating uncontracted index in the. Yes.
The mu index. Yeah. That the reason is that in fact there are two floating indices. One is mu, and another one is hidden because I wrote them implicitly. I just suppressed all Lorentz indices. Sorry, all spinorial indices. But there is a floating spinorial index there in gamma. The reason is that you derive, as we will see in this equation, by varying an action, which is Lorentz invariant, with respect to the gravitino field. So you're varying something which is Lorentz invariant with respect to the gravitino field. So the field equation must have as many free indices as the gravitino field. Because you're deriving this, You see, by varying some Lorentz invariant action with respect to the gravitino field. So the free indices will be mu and alpha. Mu and alpha that you will see, which is the raw index of the gamma index. Okay.
So there would be two indices there, one of which is being contracted with the
Yeah.
and then the other one's
Two indices in gamma, one is contracted inside, yeah, but it's useful to write them explicitly. So let me write them explicitly.
yeah, sorry, I suppose all these index actions are familiar, but not all together all at once.
I know. Too many indices can be harmful. Yes. No, of course, then, when one is not familiar with this notation, then. Okay, then you have the gamma, nu, alpha, alpha beta, and then here in let's write it like this. Psi, from beta, okay. No, in fact, the rho psi sigma beta. Okay, this is written in explicit indices. You see, the three indices are alpha and mu.
Yeah.
Because this is going to follow from delta S over delta psi alpha mu. And you see it's going to be alpha and mu indices. Okay. Now we're going to do that. Okay. So in order to describe in a consistent way a massless spin-free half field, this has to be associated with a gauge invariance, okay, which is needed to decouple the unphysical components, okay, the gauge components. Now, in curved space-time, the equation simply generalizes in this way by replacing ordinary derivative by covariant derivative, the same covariant derivative I discussed, I defined in the previous slide. You see, you can write this equation in an equivalent way. Okay? Now, consistency would require that the unphysical longitudinal components, as we said, okay, decouple in curved space-time as well. However, if we covariantize the gauge transformation, the above the gauge transformation by replacing ordinary derivatives by covariant derivatives, this is the only way to covariantize it. Okay? You see that this is no longer a symmetry of the equation. Because while this was a symmetry of the Schrödinger equation, because you see, ordinary partial derivatives commute. Covariant derivatives do not commute. They do not commute. And in fact, you have that d nu acting on some field phi, whatever, is nothing but the Riemann curvature tensor acting on the same phi, okay. The Riemann curvature tensor are acting on the same field phi, the main. You can verify this equation. Just check, just compute d nu on psi rho acting on psi rho. Okay? Do this exercise, you will find the Riemann tensor, okay, acting on all the indices of this guy. There are two indices. One which is stressed. There is an alpha index here, which I expressed, okay? And there is a rho index. And you will find the curvature acting on both indices. So you will find R, mu, rho, sigma, psi, sigma, alpha. Curvature, you know that the curvature has four indices and then a couple of indices. This is one of these acts on the space-time index. Plus curvature acting on alpha. Curvature can be given a couple of indices in the Lorentz group, in the Lorentz algebra, AD. Okay? This you can do by starting from this one, from the general definition of Riemann tensor, and changing the last two indices from space-time indices to rigid indices using the field bind. Okay? Then what you find is that this has to contract with the spinorial representation of the Lorentz group acting on this rod. Okay? So this is the action on the space-time index. This is the action on alpha. The one is done in this way. The other one is done using the local Lorentz generators. SJAD is equal to 1/4, gamma, or back to 1/4 gamma A, gamma B, anti-conductor. You can verify that this is the spinorial representation of the Lorentz generator JAD. So this is the way, this is the commutator of two covariant derivatives on one field. Is R in a suitable representation on the field, acting on the field. Okay, this action on space-time indices is this. The action on local Lorentz spinorial indices is like this. Okay, so you see they don't meet. Yes.
Maybe you said before the emphasize RBU, there is not a rigid tensor.
Oh, I'm sorry. No, it's not a rigid tensor. No.
You cannot specify the other two components.
Yeah, I cannot specify that. Thank you. It's not. This is the Riemann tensor. This is the Riemann tensor. Okay. This is the Riemann tensor. Just
Make it is confusing if people see it.
No. I totally agree with you. I mean,
So I know some of this is.
yes.
But that's your point.
No. It's important. R. The Riemann tensor, no, is a function of the affine connection, mu rho sigma, and we define like d gamma mu rho sigma minus d mu gamma mu rho sigma and plus blah blah blah. Then there are other terms. Okay. Now you can turn these indices. So you split these indices in the first couple, which is anti-symmetric, and in the second couple. Okay. Now this is if you want this asymmetric, and in the second couple. Okay. Now this is if you want this second couple, we find the action on the vector fields, on the tangent space. Okay. The second couple. Second couple define a linear action on the vector fields in the tangent space. Right. So if you have a vector field on a tangent space, you know how to transform it. If you go around the path, okay, it rotates like this. But then you can also write this mu AD. You can turn these two indices in rigid indices using the field bind. And you can verify that this is equal to omega mu AD. You can verify that these two are equal. Where R omega, how is it defined? R omega mu AD is defined like this. Mu omega mu AD BA minus d mu omega mu BA, okay? Plus omega BC mu omega C A mu minus omega B C mu omega C A mu. Okay, this is the definition. You can verify that these two are just the same. How do you verify this? Using the first field binding postulate. Okay? D mu v mu a is equal to 0. You do two derivatives and you integrate them, you get this has to be 0, but the commutator of these two covariant derivatives is expressed as the sum of two acting on this and this. Since it has to be 0, these two are equal. Okay? So instead of writing the Riemann tensor in terms of gamma, okay, where this is the torsion for gamma, this is the torsion for gamma, it's much more convenient to write the Riemann tensor in this way using the spin connection. So this is the curvature associated with this gauge field, spin connection.
So that's kind of like you normally see the field strength in your
Precisely. You have a gauge field and you define the field strength, like in electromagnetism. Here we have a gauge field, omega, AB. AB are the internal indices. They are true internal indices, AB, okay, associated with the current. So this is really a gauge field strength. The field strength associated with the gauge field. The gauge field is omega. It's a true gauge field.
So when we took that commutator of the covariant derivatives there, we got two terms, I think on the other board, we got two terms, the ones associated to curvature of space-time, and others associated to the gauge, the kind of field strength.
Precisely. And the result has to be 0, so that's it. The result has to be 0. But this is all in my notes right here. D nu, D rho, A. Using the formula here, we have to act by means of this R on all indices. This is R, gamma, rho, sigma, gamma, V, rho A, okay, sigma A, plus I have to act on A, but the action on A is defined by this guy. AB. And this has to be 0. So here you get the relation between the two. They are the same. If you want, you can do the explicit computation. That's a bit lengthy, but you get the same result. Both are in the if you want, they are on the lecture notes. Sure. Okay, good. Let's have a break then. Yes, sure.
So we can do this, like, we don't need to say that we are working with the
Sure.
So we can do this, like, we don't need to say that we are working with the delta protein, right? We could do this for any general spin event, right? We could do this for any general spin event.
Any.
The information that we are working with is contained in the covariant.
The information that we're working with a spin-free half field.
That we are working with supergravity.
That's in the. It's coming now. It's in the covariant. Precisely. It's in the covariant. You see this part. Now, for a later figure, no other investors. So it is inconsistent by itself because it has to be right. Otherwise, you will have non-physical laws entering and affecting the physics, and you don't want that. So you want this spin one half component, we have component covariant. So this has to be a symmetry of the theory. But it's not a symmetry of Rayleigh-Schwinger as we shall see. It's going to be a symmetry of Rayleigh-Schwinger plus gravity. And that's supergravity. So that's the first important exercise I will suggest you. Take the Lagrangian I will give you, Rayleigh-Schwinger plus gravity, and prove that it is invariant under this transformation. And so that it is consistent. I mean, in order to define a massless spin-free half field on a curved space-time, You need to couple it to gravity. Another way of seeing it is that this is supersymmetry. And a theory invariant under supersymmetry should describe the supersymmetric multiplet, a multiplet with respect to supersymmetry. That is the minimal representation of the supersymmetry algebra. And the minimal representation contains spin 3/2 sp. So you cannot make a theory invariant under a group, okay, if it does not contain at least a representation of the group. It has to have a representation of the group. And the minimal representation contains spin 3/2 and the spin 2.
In the initial part of the presentation, like what did you show that if you incorporate supergravity, and then it turns out to be if you incorporate supergravity, and then it turns out to be invariant in a different places, so it must have some kind of general relativity inside.
Yeah, it's a necessary condition. Yeah.
So let me get this straight. If you have a field theory and you make it supersymmetric, then it must have gravity in it.
If you have a field theory, you make it locally supersymmetric. Because you see, here it's important that the supersymmetry is local.
Yeah, because
Otherwise, you get invariance under global space-time translations. But global space-time translation is not
just lose all
an invariance of general relativity, it's invariance of Young's theory of any non-gravitational theory. You see? So this is really implied by local supersymmetry itself.
Field theory plus local symmetry equals field theory plus gravity.
Field theory plus gravity. This is a necessary condition. Now, from here to construct supergravity theory, there's a lot of work to do. And the first to do this were these three people, Ferrara, Friedman, and Van Nieuwenhuis, in 1976. And the calculation they did was tremendous, was enormous. So it's not so easy. they did a very, involved calculation for which they used a computer. Now in 1976, computers were not really that developed. They were really very basic, but they were using some very basic code. And they could manage to work out all these computations with connections everywhere. And they did it. But then afterwards, there's being showed them that it is very easy to do the same calculations in another way. That's always the case. So, yeah, it's very frustrating. Yeah, but they came after. So the credit goes to the system.
And is there a reason why the occasionally
Yeah, it's the same reason why the longitudinal mode of the H field of electromagnets are the physical and the charge is, if you have a massless particle, no, then you can only two states. Because at least you only define the spin is the projection of spin along. If I can have just two states, this, yeah. So, but if you count the states in a spin, we have multiple C2, we have plus, we have plus minus that both. But you want two states, the two felicity states for a mass system. So you have to get rid of plus one half minus one. And these are felicity states for epsilon. So you can get rid of them by choosing the epsilon. You do this transformation between mu epsilon, you get rid of them. Okay.
trying to stabilize it. One facing one way. These tools and this wall. How do we use the statements for the
I have no idea. The default is 1.3.
Is it two K?
I mean, it's actually good, these things are pretty clear. So it's better, I think, to reduce after the fact.
Oh, this. Actually, that's a good idea. There's also some of the shots that kind of zoom in so much, so maybe closer to zoom in instead of zoom out. Okay.
And I think I've got enough space for, one program doing this, so, worst comes to worst, I just keep copying, get out there.
Oh, yes,
Connection, right? Yeah, let me see if I can connect.
yeah, this is called, no, this one. Oh, yeah, okay, Wi-Fi, touch, yes.
Task, yes. Okay.
Touch is not one for.
Ah, okay.
Now, it was on 12 university, some of the oldest.
Ah, I see, I see.
Do you have to enter some? Yeah, sure, just you can put your.
Name.
Name and, I put my number. I put my number. They don't send you a message. You don't need to do this, remember, I think it's.
No, I don't want.
Uh,
version. Yeah. Okay, okay, we can resume. Okay, so we wrote the Rayleigh-Schwinger equation in curved space-time, basically covariantizing that on flat space-time, replacing ordinary derivative by covariant ones. But then what we need to require in order for psi, the gravitational field, as a massless field to be consistently defined on a curved space-time as well, is that we can decouple its longitudinal modes, which are, we have to require this. So we have to associate with it a local invariance, gauge invariance impose of this form here, defined by, parameterized by a spin 1/2 parameter, local spin 1/2 parameter, just as it we had in on flat space-time. Okay, this is needed for the description of consistent description of the gravity as a massless field. However, as you can see, in curved space-time, the Rayleigh-Schwinger equation is no longer invariant because the commutation of two covariant derivatives is not zero. They don't commute any longer. Okay? So this is a problem. So Rayleigh-Schwinger alone does not describe consistently a massless gravitational field. However, notice that this gauge transformation, which is associated with gravitational field, for its consistency, okay, is not in fact a local supersymmetry transformation. It's parameterized by a local spin 1/2 parameter. So it is a local spin 1/2 supersymmetry transformation. So whenever you have a massless gravity, you have a local supersymmetry, and vice versa. Whenever you have a local supersymmetry, you must have a local a massless gravitational field, which is the corresponding the gauge boson. Okay, so gravitational field to be consistently defined on a curved space-time. Now, therefore, as I said, a consistent definition of the gravitational field on curved space-time requires invariance under local supersymmetry. Now, as we've seen, Rayleigh-Schwinger alone in curved space-time is not, but a theory combining the gravitino and the gravity field, that is a theory, gravitational field in which gravity is coupled to gravitino, is invariant. So if we couple gravitino to Rayleigh-Schwinger field to Einstein gravity, as we shall see in a moment, then the theory is invariant under supersymmetry, and therefore it can describe consistently a massless spin 1/2, a spin 3/2 massless gravity, because it is invariant under this supersymmetry transformation, that is the corresponding gauge transformation. Now it is convenient, the corresponding gauge transformation. Now it is convenient, before proceeding in this direction, it is convenient to write down an action density for the gravitational field. You can easily verify through this that starting from this Lagrangian density and deriving with respect to the gravitational field, you end up with this Rayleigh-Schwinger equation. That's easy. You verify the gravitational field, you get two terms, but these two terms are using the properties of the gamma matrices. Okay, so you write them in terms of a single term. Okay, in which the variation of the gravitational is leftmost position, then you drop it. And then you get your Ritter-Schwinger equation. So I suggest you to prove this. Yeah.
In the previous slide, the last time, the gamma is 3 indices.
Yeah. Now there is a 3 index term. You see, this gamma has 3 indices. These two are equivalent because of a property of gamma matrices that I'm going to write down. You can easily prove that with some gamma matrix algebra. Gamma 5 for me is I times gamma 0, gamma 1, gamma 2, gamma 3. Okay? And that is equal to, now in the basis I'm using, minus 1, 1. I'm using a basis which is a Weyl basis, the Weyl representation. So gamma 5, you can easily deduce from this that gamma 5 times gamma A, B, C, or nu rho is equal to square root of G. This is square root of the determinant of the matrix times epsilon mu rho sigma gamma sigma. Check this. Now, if you use this property, here. I use here E, but what is E for me? E is the square root of the absolute value determinant of the matrix. E is the square root of the absolute value determinant of the matrix. This is my definition of E. This E. Okay.
Maybe was the question, what is the definition of gamma mu rho? And this is
Oh, I'm sorry. Yes. Gamma mu rho. Yeah. This is the 3 times antisymmetric. So it's gamma mu, gamma rho, antisymmetrized. So this is equal to 1/6 times gamma mu, gamma rho. Yeah, sorry. Plus all permutations with the plus or minus depends on the sign of the permutation, right? So this is gamma mu. When I write gamma mu here, this is 1/2 gamma mu minus gamma mu. Yeah, this is the usual. Okay, so we can. It is useful to write the Lagrangian density in terms of a Lagrangian 4 form. So to use the exterior form notation because it's easier to. It makes invariance under diffeomorphism manifest, and it's easier to vary with respect to various fields using the exterior form notations. Okay, you suppress a lot of indices. You make your life simpler with the exterior form. You see, so it's a more compact form. You write the Lagrangian I've just written in the previous slide. Okay, times the 4d4x. Okay, the volume element of Minkowski space, of your space-time d4x as a 4 form. The square root of the determinant of the matrix, which has to be is in the definition of L4 LS RS. Okay, this is the definition there. So this is a density, Lagrangian density. So the 4th form, the Ritter-Schwinger Lagrangian density, has this expression here. You can verify this. I suggest you to check this. You have to use these properties. You see, And in particular, this relation between dx nu, h dx nu, h dx rho, h dx sigma with the volume element. There is an epsilon symbol there. Okay? And our convention for the epsilon symbol is simply that. The epsilon symbol is always a constant, plus or minus 1. It's different from 0, where when all indices are different, and it's totally antisymmetric. And our convention is that epsilon 0, 1, 2, 3 is equal to minus epsilon 0, 1, 2, 3, and is equal to plus 1. From this, you deduce the expression of all the others. Okay? So try to do this exercise. You clearly see that dA, wedge dB, wedge dC, wedge dB is nothing but minus the square of the determinant of the major times epsilon times using the notation above. Okay? In case you have any problem, we can work it out together. Okay? Okay. Now, since we're going to couple it with gravity, it is useful to write the Einstein-Hilbert term in the same way, namely in the exterior form notation. So we write a four-form Lagrangian density. The Lagrangian density of the Einstein-Hilbert Lagrangian is this one. With K is defined, I hope I defined it somewhere here, no. Kappa is square root of 8 pi Newton's constant. Okay. We're often set it to 1 in our calculation, but here I'll keep it explicit. Okay, this is the Einstein-Hilbert Lagrangian density. As a fourth form, I suggest you put that it is written in this form. So it's a good exercise to check that this and these are related. This is the definition of the Riemann tensor, as I gave earlier. And this is the Ricci scalar, when you contract all indices. Okay. Okay, now we want to put these two ingredients together. Spin 3/2 field, spin 2 field. And prove that the combination is invariant under supersymmetry. So, pure n equal 1 equal 4 supergravity. We put these two terms together. Okay? We get a single Lagrangian density 4 form, which has this form here. Okay. There is a bracket. No, well, there's a bracket there, but it doesn't show. Okay. So it was derived by Tezer and Tonino in 1976. So what does it mean? Let me consider the spin connection omega to be an independent field. Just an independent field. We know it's a composite connection because the condition that on the torsion, that the torsion is not dynamical. This is one of the assumptions that we're using here. The condition that the torsion is not dynamical fixes omega in terms of the field line and as we shall see of the gravitino field. Here we're going to have another condition, a torsional condition, but which fixes omega in terms of all the other fields. Okay, but let's not update it now. Okay. So we consider connection as an independent connection. So we have as an independent field. So we have three fields: omega, psi, d. Gravity, gravitino, omega. We vary with respect to them. We first vary with respect to omega and derive the equation of motion for omega. If we vary with respect to omega, what is omega? Omega is in R, is RAB. It's much easier to use the exterior formulation. And then vary omega by infinitesimal quantity, delta omega b. And then use this property that you can easily verify that the variation, the infinitesimal variation of the Riemann curvature, RAB. RAB is the Riemann curvature, is a two-form. Recall what the convention that were given in the previous slide. RAB is not the Ricci scalar, the Ricci tensor, but it's a two-form, which is R mu nu AB dx wedge dx divided by 2. Okay? Now, if you vary this, you get variation to the covariant derivative of the variation of omega. Then you integrate by parts, and you find this way. When you integrate by parts the Einstein temperature, the derivative hits the theorem. Here it is. Okay? Then you have an omega in the covariant derivative of psi in the second term. Remember, the covariant derivative of psi has an omega inside. So you have two terms. And you can easily verify that that this equation can be written this way. Now, this condition can be interpreted as that the super torsion defined by this combination vanishes. This combination is called the super torsion. This is a supersymmetric torsion. Okay, but in terms of the torsion, this is telling you that the torsion is different from zero. This is typical in supergravity. In supergravity theories, there is torsion. The connection is generally this torsion. This is typical in supergravity. In supergravity theories, there is torsion. The connection is generally this torsion. The reason is that how do we define torsion? The covariant derivative. What is this? This is d nu A. I'm not anti-symmetrizing here. So minus gamma G mu rho V rho A plus omega A D mu D E mu. This is the definition of T. Okay? This is recall that this is the Levi-Civita. This is symmetric, Levi-Civita symbol. This is symmetric. There's no torsion here. Now this is equal to twice. No, sorry. Yeah, this is equal to what was the contortion. The contortion tensor. Okay? Whatever you find on the right hand side is the contortion tensor. If you anti-symmetrize, this goes away because this is symmetric. So if you anti-symmetrize, so you compute this guy. Now this is nu are anti-symmetrized. This drops out, and you get dA plus omega AB wedge dV, which is this term written in form notation. This written in form notation. This is equal to this anti-symmetrized, but this is the torsion. Okay, so whatever you find on the right hand side, this is the torsion. This equation is telling you that this is equal to I over 2 psi bar gamma A psi. So you have torsion. Of course, how do you solve this equation? This equation can be solved in omega. Okay, so you solve this equation by writing omega as a function of the feedback side. There is the details of how you solve this equation. Well, it's straightforward, but you can find on the lecture notes. But I can show you later if you want. Okay. Okay. So to derive this equation, I'm using these properties of the gravitational field. Okay. Recall that the gravitational field is a one form, as written here. It's described as a one form. This means that its space-time index is contracted with dx. Psi is psi mu alpha dx mu. So I'm suppressing alpha, and mu is contracted with dx mu. So it's a 1 form. It's a 1 form. This is a class, it's a commuting variable. So psi alpha, psi beta is equal to psi beta, psi alpha, because we have two minus signs. One when we swap the components, the other when we swap the dx mu. So it's a commuting variable. Then we have these properties, okay? And using these, you can prove that you get this torsion equation. Okay, so you do consider omega as an independent, you work out the corresponding equation, and the corresponding equation fixes in terms of the psi. In the second order formalism, what you would do, you start from this guy, this equation, you solve it, you plug it, the solution, omega, inside the Lagrangian, and then you work out the equation of motion for that. So you start from considering omega not as an independent variable in the second order formalism, but already as a function of psi and b. Okay.
Some people like 1.5. Okay.
1/2, yeah. Now I'm coming to that. Yeah. Now I'm coming to that. Now the solution is a function of psi, but in the second order formalism it's even more complicated because you start from a torsionless omega, and then you have to work out also the higher order Fermi terms. As I'm going to show here, you don't need that because all the higher order Fermi terms, the order 4 Fermi terms in the Lagrangian, which you always need, they can be incorporated in the definition of omega. So the action does not contain them if you choose omega to be a torsion full connection. So you can reabsorb all these terms in a redefinition of omega. This is typical of pure n equal to 1. In generic supergravity, this is not the case. You cannot reabsorb the order 4 terms in the fermions, which are the most complicated ones, in a redefinition of omega. In this case, you can. And things are much simpler. Okay. So you can split omega into a torsionless one, solution of dv equals 0, plus something else, which depends on psi, so on torsion. Okay? You can always do that. Okay. Now, what I suggest you to do is to check that this equation, this action is invariant under local supersymmetry. This is the supersymmetry translation that we want to demand, sorry, the supersymmetry invariance that we want to demand, okay, for a consistent definition of the T. Okay? And check that everything is consistent, provided V, the feedback, is not according to that law, okay, as this transformation property. Okay? How do you prove this? First of all, why do we need K? Before I didn't write K, kappa. I didn't write kappa. Why do we need kappa? Well, we need kappa because let's talk about dimensions. Epsilon has dimension of length to the 1/2. It's half a length. Because epsilon bar gamma a epsilon 1, 2 is a length. So it has to be. Now, from the Ravita-Schwinger field itself is length the minus 3/2. This is the physical dimension of psi. So this means that psi mu dx mu. We multiply times the length, dx mu is the length. This is L to the minus 1/2. Okay. So this means that if we want to write delta psi mu as d nu epsilon, okay, like this would be inconsistent dimension because this is length to the 1/2, this is length -1, this is length to the -3/2. So it's not okay, not good. I have to multiply times 1 over kappa, length -1, because kappa is the dimension of a length. So you need that in order for the dimensions to come out well. So what you do, you vary the action with respect to the various fields. Okay. Now you can do this in the second order formalism, in the first order formalism. In the first order formalism, how would you do that? Well, you would have to work out the supersymmetry variation of all the three fields which are independent in the first order formalism. That is V, psi, and omega independently. Now there is another formalism which is called 1.5 order formalism, which is a shortcut. Well, it's a trick, but it's a useful trick. So you vary the Lagrangian with respect to all the three fields as if they were independent. But then after you did this variation, okay, after performing the variation, you replace omega AB by its solution, the solution of its equation. Okay? If you do that, you see that the first variation cancels, because the first variation is proportional to the variation of the action with respect to omega, but this is the equation of motion of omega. You have solved it. If you plug in the solution to the equation of motion, this is zero. So you don't have to bother about devising a supersymmetry transformation for the connection. You don't have to bother about the connection. Just vary S with respect to psi. Okay? And use for the connection solution of the supertorsion equation. Okay? So this is something in between the second order formalism and the first order formalism. So you do that, and I suggest you to perform this calculation and check that it is invariant. If you want, we can work it out later together. Okay, it's not so difficult. It's important to use certain relations which allow you to write products of psi in equivalent weights. These are called fields identities. They are, well, I give you the main fields identities here that you can use. You can find in the lecture notes. The main fields identity is one involving a product of two psi's. If I write psi bar, what is this? This is a matrix which has two indices, alpha and beta. And the fifth identity is telling you that this, which is a 4 times 4 matrix, can be expanded in gamma matrices. So this can be written as 1/4 times psi bar gamma A psi. This is a number times gamma A. This is a matrix. Alpha minus 1/8 psi bar gamma A psi. Okay, gamma A. You see, you're expanding in matrices, and these are the only two terms that you can use. Right? Then there is another equation which is important, identity which is important. Psi times psi bar gamma A1 AK psi equals 0. That's another one. Okay, use these properties. Okay, and then you can prove the invariance of the action. This is very useful, instructive calculation. Now, you see, in this action, apparently there are no 4 Fermion terms with 4 order 4 in Fermion. However, they come out if you write the connection as a torsionless connection, depending only on D, plus all the rest. The rest will depend on torsion and depends on psi. Now, if you write all covariant derivatives in terms of covariant derivatives with respect to this first omega circle, the torsionless one, then the second term will produce four Fermion terms. Okay, and the equation, the Lagrangian becomes ugly, of course. Okay. So 4 parameters are needed for the construction of a supersymmetric, locally supersymmetric action. Okay, are there questions? Now let's briefly discuss a first variation, a simple variant, the simplest variant of the pure n=1 4-dimensional supergravity, which was constructed by Paul Townsend in 1977. Okay, just 1 year after, and it amounts to adding a cosmological term. That's it. You see this term here, proportional to the volume element. This is a cosmological constant. So adding to pure n=1 equal 4, a cosmological constant. Now, what's the advantage of doing this? Well, first of all, the pure n=1 equal 4 supergravity has just one vacuum, which is the Minkowski vacuum. Okay, this actually now is a non-trivial vacuum, which has a cosmological constant. As we shall see, it's going to be an anti-de Sitter vacuum. Okay. So somehow it's not interesting. Paul Townsend proved that if you want to add a cosmological constant, you have also to add other things. Otherwise, symmetry will not be, the action will not be supersymmetric. Particularly, if you're going to add, you have to add this other term, okay, which is quadratic inside, as this form here. As we shall see, this is a master for the derivative. And you have to add also a term here in the variation, specific variation law of the derivative. They all depend on some parameters I call beta, sigma, alpha. If you write down the action of this form with the variations of this form, you can prove that the action is invariant. It's invariant under these local supersymmetric transformations, provided the parameters are related in this way. And in particular, provided beta is -3 lambda squared. Lambda is a real number, so beta has to be negative. So you cannot construct you cannot any cosmological term, any cosmological constant. You cannot put any cosmological constant here. The cosmological constant has to be negative. Okay? This is strictly related to the fact that only anti-de Sitter vacua, besides Minkowski vacuum, can be supersymmetric. De Sitter vacua can never be supersymmetric. I will give another proof of this later, but this is simplest. This is the simplest. You work out the calculations, you prove the invariance of the action, and you see that beta has to be negative. Now, to prove the invariance, okay, you need to use the Pierce identities. It's useful to use again the 1.5 order formalism, okay, using the fact that the equation for omega is the same as before, because the new terms don't contain omega, so the equation of motion for omega is the same as before. And it's telling you that you have a torsion, depending which is bilinear inside. You solve it just as you did before, and then you use the second order formalism to vary the action as if the three fields were independent, and after varying, you plug in the solution of this equation in omega. Okay? In case you have any problem in solving these exercises, you just ask. Okay, we can work them out together. Okay, so you plug in the solution to the condition that you find on the parameters, so that you write parameters in terms of the single parameter lambda as Townsend did. Okay. And we notice some general features of this action. First of all, you have a cosmological constant, which is negative. The in the Lagrangian, you you see that is a master. It's a master, it's quadratic inside. It's a master for the gravitino field, and the gravitino mass is lambda. Now, this does not mean that the gravitino field is massive, because this mass term, this mass that you see here, which is equal to lambda, is the Poincaré mass. The mass term that you would write if the equation of motion were written in a flat spacetime. However, as I will show, the vacuum is not flat spacetime. It's anti-de Sitter spacetime. Okay? And masses of the fermion fields in anti-de Sitter are shifted with respect to the masses in flat spacetime, okay, by a term depending on the cosmological constant. So that, although it seems that the gravitino is massive from the Poincaré point of view, but in anti-de Sitter, it is masses. This is precisely the value that the gravitino mass must have in order to be massless in anti-de Sitter. And this is an additional term you need to add to the variation, specific variation of the gravitino field. Why is this example useful to us? Because this is a kind of prototype gauge supergravity. It's not a gauge supergravity because there's no internal gauge symmetry. However, you see from here some features that we will encounter when dealing with the gauge supergravities. First of all, in order to add a scalar potential, here there's no scalars, so the scalar potential is trivial, it's a cosmological constant. So in order to add a cosmological constant, okay, you need to add a fermion mass term and an additional term in the supersymmetry transformation property of the fermion fields, which we will call fermion shifts. Okay, this is going to be true also for gauge supergravities. In gauge supergravities, in order to introduce a scalar potential, and this is implied by the gauge use, mass terms for the fermion fields and additional terms in the supersymmetry transformation of the fermion fields, the fermion shifts. Okay, precisely as in this very simple model. Moreover, there is a relation between the cosmological constant and the coefficient of this fermion shift. This precise cosmological relation we will encounter in a more general setting as the so-called potential word identity. Okay, relating the scalar potential to the fermion shift in a more general setting of gauge supergravity. Okay, so let us remember this very simple example. Let's consider vacuum. What do we mean by vacuum? What is the vacuum? Okay. By vacuum solution of a supergravity theory, we mean maximally symmetric spacetime. Maximally symmetric spacetime cannot have fermion fields on it, because fermions would break Lorentz impulse. Maximally symmetric means that Lorentz group has to be anisometric. Okay, if there is a depth of a fermion field, that would break Lorentz. Okay, so Lorentz field, fermion fields, they have to be zero on the vacuum solution. The vacuum solution is a bosonic background. All fermions are zero. All vectors are zero because a vector would break Lorentz invariance, okay, of the solution. So Lorentz group has to be a symmetry of the solution of spacetime. Okay. And moreover, if there are scalar fields, they have to be constant because the gradient of a scalar field would break Lorentz invariance. Okay. So scalar fields, if they exist, they can be non-zero, but they have to be constant. In this case, we set psi to zero. The Einstein equation, we can easily show that admits this solution. For the Ricci, this is the Ricci tensor. This is the Ricci tensor. Okay? But this is the anti-de Sitter space. This is the Ricci tensor of an anti-de Sitter space, which can be described in a five-dimensional flat space as this hyperbola. You can easily show the anti-de Sitter space is the solution to this equation. So locus of points satisfying this equation in a five-dimensional flat space, okay, with a matrix of this with these signatures, two pluses and two minuses. If you write it like this, you immediately see what the isometry group is. It's SO 2,3 anti-de Sitter. Okay, and L. So this kind of big rotation of a sphere, a big rotated sphere, if you want, okay, of radius L, and our L is 1 over lambda. L is called the anti-de Sitter radius. So this solution has a vacuum which is anti-de Sitter, and this vacuum is supersymmetric, so it preserves all supersymmetries. Okay. Are you familiar with this description of anti-de Sitter space? Okay. There are three kinds of vacuum, maximally symmetric backgrounds you can have, depending on the cosmological constant. You can have either de Sitter with positive cosmological constant, Minkowski, or anti-de Sitter. In this case, you have anti-de Sitter. For lambda going to 0, you retrieve any pure n equal 1 equal 4. And if you set lambda equals 0, you get flat Minkowski. Okay, so this is the limit in which we go the theory. Okay?
Is there a statement, you define the vacuum as maximum symmetric solution? I guess that's also the lowest energy, some definition of energy in
Yes.
So these concepts correspond, right?
These concepts correspond. You can show that you can define an energy, and that all energies of all solutions to this theory are above the lowest energy, which is the one associated with the vacuum. This was shown by Gibbons and Hall, if I'm not wrong. They extended the positivity theorem proven by Witten in 1981. They extended to anti-de Sitter. They proved that this theory, anti-de Sitter, is the lowest energy one. Then energy is it defines a lower bound for the energy.
Does this require symmetry?
Sorry?
Does it require symmetry? So what I mean is, if you take the general GR,
Yes.
does the same statement apply that the lowest energy solution would be maximally symmetric?
No, I mean, to prove this, you need asymptotic killing spinors. These are used for the proof. The existence of asymptotic killing spinors for the proof. The existence of asymptotic killing spinors so, for instance, you find models with anti-de Sitter vacua which are unstable. So, but these are non-supersymmetric. But if you have a supersymmetric anti-de Sitter vacuum, that's stable for sure, because you have the ingredients that you need to prove the possibility that is local asymptotic killing spinors. So there are few examples of non-supersymmetric, very few examples of non-supersymmetric perturbatively stable anti-de Sitter vacuum. Most of them are unstable. So this means that fluctuations of fields, they are tachyonic. So they destabilize the vacuum. Okay. Is this clear so far? Okay, so supergravity is also, so far we focused on 4 dimensions, but we can define supergravity theories in higher dimensions up to 11, no more than 11 dimensions, okay? For instance, in 10 dimensions, we have 10-dimensional supergravities, and these have the interesting interpretation as describing the low energy limit of superstring theories. Superstring theories are naturally, by consistency, defined in 10 dimensions. Okay, you have a number of them. Okay, and their low energy description is captured by a 10-dimensional supergravity theory. But you have also an 11-dimensional supergravity theory. That is a unique supergravity theory you can write in 11 dimensions. There's just one 11-dimensional supergravity. It has 32 supercharges. By supercharges, I mean conserved conserved supersymmetries. okay, supersymmetry component. So this means that the most general supersymmetry parameters contains 32 independent functions, okay? So 32 supercharges, so there's 32 conserved supersymmetries. Now, this 11-dimensional supergravity was constructed in 1978 by Kremer, Julia, and Scherk. Okay? And it is conjectured to describe the low energy limits of a microscopic theory, whose definition is so far unknown, the so-called M theory. So while having the definition, microscopic definition of superstring theory in terms of vibrating strings, okay, vibration modes of strings, we don't have the microscopic description of the microscopic degrees of freedom of this conjecture, the M theory. We only know that it lives in 11 dimensions. We only know that its low energy limit is captured by the low energy, by the unique 11-dimensional supergravity. Okay, but we don't know what are the microscopic objects. Okay, so the ultraviolet description of M theory is unknown. M theory was conjectured in the 90s by Witten, okay, as a missing ingredient needed to complete a duality picture, okay, of string theories. So it's useful to have this picture in mind. Supergravity, when it describes, when it's related to as a low energy limit of superstring theory, describes the macroscopic description. It provides the macroscopic description, you see, of those microscopic degrees of freedom which are described by superstring theory or M. Okay, very much as thermodynamics provides large-scale description, okay, of molecular models, okay, which are described from a microscopic point of view by, for instance, kinetic theory of gases and so on. Okay, so there is this interesting, if you want, analogy to bear in mind when working with supergravity. Now, supergravity theories in many dimensions are not always associated with string theories, or do not always describe low energy limits of superstring theories. Okay, but when they do, I mean, this picture holds. And when they do, supergravity provides a valuable approach for studying properties of superdeep string or entities like vacuum and the dynamics of modes around this vacuum. Okay, the dynamics of fields around. So, are there any questions? Yes.
Is there a D equals 12 theory with signature 10.2?
Sorry?
Is there a D equals 12 theory with signature 10.2?
10,2.
Yeah.
There could be, but a theory like this has been constructed recently by Leonardo Castellani. He wrote down a gravity theory in 12 dimensions with signature 10,2. You can, because the spinorial degrees of freedom, you can write a Majorana while spinors, so you can this work, Leonardo Castellani did some constructed gravity theory, consistent gravity theory. Now, whether this describes any F theory, I don't think so. I mean, it's totally clear. It's totally clear. But it would be nice, I mean, to have a supergravity description of this kind. Yeah, the only supergravity I know in 12 dimensions was this work constructed. This work here. It was constructed recently, a few years ago. Yes, I would say so. Yeah. Somehow, yes. One is tempted to yeah. Yes. I would agree. Yeah.
So it's important for this signature change, so that the signatures still have the appropriate.
Yeah.
So you have to go higher by including more directions, higher than.
In principle, but changing, you could. The important thing is that the number of spatial direction minus number of time direction has to be a multiple of 8. A multiple of 8. So 10 dimensions with the one time direction is fine, because 9 minus 1 is 8. Because that's needed in order to have a Majorana file. However, sorry, but there is a problem. However, as you go up, then you have more than 32 spinners. That you cannot do. No. Majorana file is SO 2,10. Majorana file of 2,10, which is the Lorentz, would be the Lorentz group there, is precisely 32 component spinner. So there is no problem. You have the right number of supersymmetries. More than 32 conserved supercharges is a problem. It's a problem because that would imply that you have to add higher spin fields, but you cannot have a consistent theory with a fine number of higher spin fields. Infinitely many. That's, I think, the statement. So going to 13 dimensions, avoid.
Well, you cannot just add a spin 4.
You have to add the whole thing. You have to add the whole thing, as in when you work out the effective theory, low energy theory of substring theory, you get a lot. I mean, you have infinitely many higher spin fields in the string spectrum, but in supergravity truncation, they are always truncated out. Okay. Any questions about this preliminary part? If you have problems in working out the exercises, just tell me and we can work together. Okay. Now, let's continue on the blackboard.
At some point, I'm also involved whenever you
Okay. How much time do we have left for this hour?
Yeah, we'll have about 15 minutes.
15 minutes. Okay. Let me just write down the main motivations behind the general introduction behind this our discussion about engaged supergravities. What do we mean by them? And so I will not use any formula now. It's just going to be. Can I switch it on? Okay. Yeah. It's just going to be a general introduction. Okay. So this was the preliminary part to set the conventions and a few definitions, and to introduce supergravity in general. Okay.
Just maybe
Yes.
quite general question. You said in 11 dimensions is a unique.
Yeah.
Are you referring to? So does this mean that you said n equals 32 supercharges is fixed, right?
Yeah.
The other dimensions won't have a variety, like a range of possible numbers of supercharges. That is
In 11 dimensions, you have just one spinor, spinorial representation of Lorentz group, which is 1 from 10, and that is the first dimensional one. It is not chiral, of course, because you're in all dimensions. It's not Majorana. It's just it's Majorana, but it's not vial. It cannot be vial. It has 32 dimensions. It's unique. So you have it has 32 dimensions. It's unique. So you have just one possible cause of the possible definition of the gravity, and that is the whole supergravity. In 10 dimensions, for instance, in Madrid and in type 2 supergravities, there you have the possibilities of having spinners, to Majorana vial spinners, but you have the possibilities of having them of the same chirality. Then you have to be theory, or of different chirality. Okay, so you have a non-chiral theory, and that's type 2A theory. So you have two maximum supergravity. But in 11 dimensions, you don't have this choice. Okay, you just have a 1 Majorana spinner which has 32 components. That's it. So that fixes the whole supergravity. Okay.
Really, for those who are not too familiar with spinors, I mean, they could probably speak that
Sure.
the dimension of a spinor representation increases with the number of dimensions. Really, for those who are not too familiar with spinors, I mean, they could probably speak that
Sure.
the dimension of a spinor representation increases with the number of dimensions. So and it increases differently to a vector, because you know a vector in 5 dimensions has 5 components, 6 dimensions 6. Of course, linearly, but a spinor goes like 2 to the
G over 2.
G over 2.
Yeah, the integer part G over 2.
Yeah, so
Then you have to impose reality conditions where they exist violent conditions like chirality conditions.
and because you want supersymmetries, you want there to be the same number of orthogonal and then that constrains your the number of dimensions you can possible. Supersymmetry or supergravity. Because the scale goes written to B and to B1 and you can do that after the 4 out of 12 with some tricks you can make. But after that, there's two means, for institution, vector component, or both.
Yeah, yeah. Yes, so this is the, and once you fix your gravitational field, which is fixed by the representation that you choose, then the rest is somehow, all the rest is fixed by supersymmetry, so the bosonic field content and everything else that is kind of in the supergravity model. Okay, so you don't have to you have a fixed amount of fields of various kinds, forms, form fields, one form, two forms, and so on. Okay, so that is fixed. Okay, so let's start from a general picture. To motivate our interest in gauge supergravities, where how they originate, okay, what they describe. So we mentioned the string theory and M theory as microscopic theories. So M theory, we don't know what it describes as a microscopic theory. Okay, so string theory we do. There are a number of string theories. Okay, now if we assume that they are quantum, well, they provide a quantum theoretical framework where to unify all the fundamental interactions, so gravity together with all the gauge interactions. Then there is a problem, because superstring theories are defined in 10 dimensions, okay, by consistency, okay, and we live in 4 dimensions. So in order to derive from these microscopic theories a model for our universe, a phenomenologically viable model for our universe, somehow we need to dimensionally reduce these theories, from 10 dimensions down to 4 dimensions, okay? Down to 4 dimensions. And this is done by a celebrated mechanism called Kaluza-Klein compactification. So go from d equal 10 to d equal 4, we use the Kaluza-Klein. Mechanism. What does it consist? Well, the original Kaluza-Klein model was a dimension reduction from 5 pure gravity, pure Einstein gravity in 5 dimensions to 4 dimensions, okay, on a circle. And the dimension reduced theory contains gravity coupled to a electromagnet, so a gauge spin 1 field. Okay? This gauge spin 1 field came from a matrix in 5 dimensions. So this Calvert-Klein picture provided a way of unifying somehow gravity with electromagnetism by describing them as components of a higher dimensional matrix. But you would dimension reduce. Okay? Unfortunately, as a unification scheme was not successful. Okay? It also produces scalars, massive scalars. So how do we perform this dimensional reduction? From 10 or even from 11 dimensions. Okay? So string theory or M theory. So what we do is we realize superstring or M theory on a background spacetime, which has this form here: M4 times M internal. The product, in general, would be a work product of a 4-dimensional non-compact spacetime, which is the spacetime we live in, okay, times an internal compact manifold, which would be smaller, okay, which could be a circle in the original Calvert-Klein mechanism. It was a circle from 5 to 4, but in general, it's a compact internal. Okay. Then what do we do? What's the dimension of this? Dimension 11 minus 4, if we come from 11 dimensions, which is 7, and 10 minus 4, which is 6. Okay, these are the two possibilities. Then what do we do? Now, we are interested in the low energy description, okay, of these theories, like string theory and theory. So, we start from their low energy description in equal 10 or equal 11. That is, we start from supergravity in equal 10 and equal 11. Okay? And we dimensionally reduce supergravity theories down to 4. This is what we do. Because somehow we integrate out all those massive string modes. So then what we do, the reduction is affected by taking a generic field in 10 or 11 dimensions, okay? Let me denote by x mu the coordinates of the 4-dimensional spacetime, non-compact spacetime, and by y alpha the internal coordinates, the coordinates of this internal map. Okay? Now, a generic field in d equal 11 or 10, okay, will be function of both coordinates, because it propagates over the whole 10 or 11 dimensional space. However, the spacetime has this form here, so we can expand this in harmonics with respect to the compact map. So we expand this like this. Where these are fixed functions, which are eigenfunctions of the Laplace operator in the internal space. So these y are called harmonics. They are like spherical harmonics, or if you want, if you are on a different geometry, like assume that they're just the Fourier expansion. Just the Fourier expansion. These are the They are eigenfunctions of the Laplace-Beltrami operator in the internal dimension, okay? In the internal space. This lambda goes like this is lambda here. So lambda goes like 1 over r, where r is the size of your internal. Okay? So you can expand in this way. And if you apply your 10 or 11 dimensional Laplace operator to phi, what you end up with is four dimensions phi n, okay, plus lambda squared n phi n times y n. Okay, if you apply your Laplace operator 10 dimensions, okay, to this field, then you have this guy. When Laplace operator acts on y, it gives you lambda squared. Now, if this is a free field in 10 dimensions, this has to be 0. This is a massless field. If this is a massless field in 10 dimensions, okay, then this is to be 0. But if this is 0, this means that for each n, this has to be 0. That is, this phi n are massive modes. They are massive modes. See? So the coefficients of these expansions describe massive fields. If you apply the Laplace-Beltrami operator to this guy, you end up with a tower of massive states. How many? There are infinitely many harmonics, so there are infinitely many of these states. You have a tower or an infinite tower of massive states. The masses are lambda squared, and they all go like 1 over r. The masses, they all go like 1 over r. For a simple example, let's consider the toroidal compactification. Okay?
The compactification over r to simplifying what the shape of the manifold is.
Oh, of course,
Many different scales.
Yeah. I'm simplifying it. R is since it is a compact manifold. We can define a global size, like the minimal pole containing the manifold. Since it's compact, you can define a minimal pole containing the manifold, and R is the size. So of this pole, the radius of this pole. Okay. So with any compact manifold, you can associate a size. Okay. And the order of these masses, okay, is 1 over r. Okay, that's the size you have. See, for example, let's consider fields on a circle. M4 times S1. You take in 5 dimensions your fields, they depend on these extra coordinates on S1. And now being an X coordinate on X1, okay, this coordinate belongs to a interval. This is the coordinate along the defined coordinate along the circle. Okay, R is the radius of the circle. So since it's a compact coordinate on an interval, you can always expand this. Fourier expand I n y over r. Okay, I can perform this expansion and running from minus infinity to plus infinity. You see that this is the harmonics on the internal space, because this is n squared over r squared with a minus sign. e to the I and y over I. Okay? So these are your eigenvalues. These are your eigenvalues. Okay? Here I would say, let's call this right minus. Okay? So recall that we are in the Moscow minus notation. So that here you have a plus. This plus here, you have a plus not a minus because this enters this with a minus sign because it's this Moscow minus notation. Sorry about that. Okay, then you apply your 5-dimensional D'Alembertian, okay, so Laplace operator, which is often denoted by a pentagon, but it's a dot square to this 5. And when you find out that this is the sum of this applied to this, okay, so this is equal to 4 times phi n. Okay, and then here you have a term in which S1 with a minus sign, so it's plus n squared over I squared phi n e to the I and 1 over I. Okay, and now you see that you have a tower of states. You have a tower of states. Now the result of the compactification, so effective four-dimensional theory, okay, is obtained by truncating this spectrum, which would be infinite dimensional, to the 0 mode, n equals 0. This means setting it to 0 the dependence on the internal coordinate. This is what you do in Calzacline. In Calzacline compactification on a torus or on a circle, you restrict to the 0 modes in the Fourier expansion. And that defines a finite subset of fields, okay, living in 4 dimensions. And this subset of fields define the theory restricted to this subset of fields is a consistent truncation. What does it mean, consistent truncation? It means that any solution of this truncated theory is a solution of the higher dimension. Okay? So when compactifying on a circle or even on an n torus, which is the n-folded product of circle, okay? So it's just the same thing. Okay? Then, after expanding all the fields like this in harmonism, fully expanding all the fields, and you set this mode to 0, so the dependence on the internal coordinate to 0. You restrict to the 0 mode. And the restriction to the 0 mode is defines an effective 4-dimensional theory, which is the 4-dimensional theory you resulting from the dimensional reduction. And this is a consistent relation. The theory describing these 0 modes, okay, is a consistent application of the higher dimensional theory, compacted data. Okay. Now, if the compactification manifold is more general, it's not a torus, but it's a sphere or other less trivial manifolds, then the issue of consistency of the reduction, that is the problem of restricting to a finite number of these modes, such that the resulting theory is a consistent truncation of the higher dimensional theory, is more complicated, much more complicated. It's a complicated issue. Okay? It's a complicated issue which has to be dealt with case by case. Yes.
What is the right side interval on y open? Y belongs from 0 to 2 pi r, right?
Y, because y is the coordinate of the circle. This is the circle, this one.
Yeah.
This is 0. Okay. So it's the affine coordinate of the circle. So you set one point of the circle to 0, you move around the circle. Okay. Y is the length of the arc along the circle from any point. So start from 0, you go round, you end up to pi r, which is the length of the circle.
But it's open over the center.
It's open because there is an identification. So you can, if you would close there, that would be overcome equals 0, y equals 0, y equals 1. You have the same point. So you would double count the same point. Okay? But it's closed. Okay? So this is the general mechanism that you use, the general way of reducing these higher dimensional theories to 4 dimensions. Okay, we shall be mainly interested in 4-dimensional compactation. Let me end up with a scheme. Now, let me end up with a scheme which we will use for our later lecture. But it's important to, it's a general scheme that is important to bear in mind. Can I use this is a general scheme. I switch on this slide. Okay, so we are in equal 10 superstring theory, or equal 11 M theory. Now, if we compactify these theories on a manifold, which is on an internal manifold, which is rigid flat, no fluxes, magnetic fluxes or field strengths, okay, that you have in the supergravity description of the 10-dimensional superstring theory or M theory, okay, across cycles of this internal manifold, so nothing, just a rigid flat manifold, like an n-torus, and product of circles. If you do this very basic compactifications, well, it's basic for an n-torus, but you can also consider the Yaw compactification, which is not basic at all. It can be very complicated. But if you do this compactification, well, what you end up with in 4 dimensions, or d dimensions, equal 4, it could be also d greater than 4, in between 4 and 10, okay, is an ungauged. So you end up with an ungauged supergravity. You end up with an ungauged supergravity. What do we mean by ungauged supergravity? Ungauged supergravity means that the vector fields, which have all masses, all fields are masses, all fields are masses. The vector fields, which are massless, and they have by consistency their own gauge transformations, are not minimally coupled to any other field. So you have a gauge group, you want into the number of vectors associated with the vector fields, but nothing is charged with respect to this group. Nothing. All fields are neutral. So ungauged means that vector fields are not minimally coupled to any other field. Okay? Now, ungauged supergravities, which will be the subject of our first part of the lectures, they are interesting in the sense that they have an interesting mathematical structure. They have some interesting features. They've been extensively studied, especially in the 90s and the later decade. Now their solution has been extensively studied. They have their pros and cons. The pros are that they feature a global group G, called G. They feature a global symmetric group G. In some cases, it's quite large. Okay, and this global symmetric group has a meaning, a physical relevance, since it contains part of the so-called string ambiguity dualities. I'll spend a few words on this. Okay, so within this global symmetric group, okay, there are contains T dualities, S dualities, and in general P dualities. So all the dualities between string theory and ambiguities. Not all of them, but part of them, important part. Okay. So the presence of this global symmetry group makes this their mathematical structure interesting, and these theories make them appealing. Okay, from the mathematical point of view. Unfortunately, and these are the cons. Sorry, the cons. There are no masses. So no way of spontaneously breaking supersymmetry. Now we live in a non-supersymmetric universe, as Sam was saying yesterday. We want to at least have a mechanism for spontaneously breaking supersymmetry. You don't want to break it manifestly in your action, but spontaneously. And you do that with masses, but there are no masses. No way. There are no scalar potential. There are several scalar fields in general. You have several scalar fields, but no scalar potential, so no dynamics. This means among these scalar fields, this means that these theories have a lot of flat directions, massless scalars, which couple to gravity. So this would imply longer length interactions, which are not observed in our universe. So from a phenomenological point of view, these theories are very bad, okay? Are undesirable because they have these undesirable features. They are not predicted. Scalar fields coupled to vector fields, coupled to p-forms, but their value is not fixed by any scalar potential to some minimum. So their values of scalar fields are not selected. Okay, so the values of all these couplings is not fixed. Okay, it's not fixed at all. Nothing is fixed. So these theories are highly non-predictive. No spontaneous supersymmetry breaking, not predictive. Nevertheless, they are interesting because of this interesting mathematical structure related to the global symmetry, which encodes string dualities. What do we mean by string dualities? Now, unifying quantum theory, the quantum theory unifying all interactions. The main candidates for these theories, which are superstring theory and M theory, they're not unique. There are several superstring theories. One M theory, but there are several superstring theories. So, how do we account for this multiplicity from this picture? From the point of view of a unique unifying quantum theory, microscopic quantum theory. Well, the idea of dualities came in the 90s, just precisely to account for this multiplicity. The idea behind duality is that different superstring theories realized on different backgrounds are in fact different descriptions of the same physics, of the same quantum physics, that is of the same quantum degrees of freedom. So they look different, but at the end they are equivalent descriptions of the same thing. Okay? And so they must have the same spectrum, they must have the same interactions, and they must have the same low energy effective theory, which are supergravities. Okay? So dualities are correspondences between these equivalent descriptions. And as correspondences, they are correspondences also between their, or better, equivalences between their low energy descriptions, which are supergravities. Okay? So dualities manifest themselves as equivalences between, in particular, between the supergravity descriptions of these two world string theories on these backgrounds. Okay? And in most cases, these dualities manifest themselves as global symmetries of the low energy descriptions. And this is why they enter this G, global symmetry G. Not all of them, but many of these dualities, like T duality, S duality, and so-called U dualities, they are part of G. There are some dualities which are, for instance, to give you an example, T duality along an odd number of directions. Okay, that is not contained in G. That is not contained in G. for example, T duality, what does it mean? It means that type 2A compactified on a circle of radius r is equivalent to type 2B compactified on a circle of radius alpha prime over r. Equivalent means that the two worldsheet theories are the same, are just equivalent. Okay? The superstring theories are described by equivalent conformal theories on their worldsheet. Okay, so they're just the same physics. T duality is an example of these kind of dualities. Okay, is an example of these kind of dualities. Okay, another example is the S duality, mapping the backgrounds with a certain string coupling constant to the background with a coupling constant, which is 1.
So, since these T dualities are also visible in supergravity, this would expect
No, not all of them. Not all of them.
So when you talk about these duality groups, they refer to
Yeah.
supergravity.
When I talk about this general duality in string M theory, I'm not talking about supergravity. I'm saying that dualities manifest themselves. So the statement is that dualities manifest themselves as equivalences between the supergravity descriptions. Equivalences. Okay. Now, certain dualities are in fact not just equivalences between two different descriptions, but are in fact global symmetries of a single description within a single description. Some T dualities are, and for example, if you take T duality, if you do T dualities along an even number of the internal direction of a torus, so you take type 2A, compactify it on a 6 torus, and you perform a T duality along an even number of directions, that is inside the global symmetry of the lower dimensional. But if you perform a T duality along an odd number of directions, like in the previous one, you go from type 2A to type 2B, and then the two descriptions are different.
But it's still using the T duality with binding points, right?
Oh.
What's the binding points? You're using the supergravity.
That's right. But when you consider supergravity, you're just truncating this out. So the lower dimension supergravity is obtained by compactifying along directions, so internal directions, but then setting all masses, so restricting to the zero mode. Restricting to the zero mode means that zero momenta and zero winding modes. They're all zero in the lower dimension supergravity. So you do the Fourier expansion, and you restrict to the zero modes in the Fourier. So n equals 0. And this restriction is always for toroidal. You end up with this amounts basically to setting all the fields to depend on the internal coordinates. Yes. You are, but you are missing also the closer line mode.
Yeah, but you still have the zero.
You have the zero closer line mode, but that would map into the zero winding mode, right?
Well,
Because you have this.
For a given circle size, the less the circle you don't have zero. Oh, sorry, zero. Just the zero one. I see.
Yeah. It's trivial somehow in this case.
Sorry. Yeah,
But if you had, I agree, if you had also momenta, then T duality would Kelvin momenta would map them into winding modes, and winding modes are not described in supergravity. For sure. Momenta, then T duality would Kelvin momenta would map them into winding modes, and winding modes are not described in supergravity. For sure. So that these are something stringy that they are not described there. So. So this is the picture. For instance, when you go from 10 to 4 dimensions, okay, and you have this characteristic group, which is SO n, n. Now, the T duality group is O n, n. So n is 6. So S is the T duality group is O 6, 6. But G contains only SO 6, 6. So you're missing all the T dualities along an odd number of directions. But that's because this would map type 2A into type 2B description. differ in the Ramon sector. So they are really different descriptions. They're not unified in this picture. But nevertheless, G contains all the other T dualities, contains S duality, it contains part of the U dualities, so it contains an important part of, this is why dualities were in the 90s were tested, famous works by Sen and others, by tested using gauge supergravities, by inspection, by comparing the PPS spectra on the two sides and checking that they matched. PPS spectra is a spectra of supersymmetric states whose properties are protected by supersymmetry. So against so if you do a non-perturbative duality, their values are not expected to change. Okay. This is the idea behind dualities, and the fact that part of this duality, part of this is in G. So
Sorry? We're going to over time for lunch.
yes, let's go. Let's go.
I don't know if you want to say something about the case or will be.
No. Let's complete the scheme with the light column after lunch.
Oh, after lunch to somebody else.
Oh no, sorry. Tomorrow. Next week.
Thanks.
Thank you very much.
Sorry for.
Sorry for.
I think there were some questions just good to raise.
Okay. Sure.
It's not that.
No, it's good that it is participated. This is important.
It's good to keep the tempo slow and.
No, because if there is no participation, I fall asleep. So it's good. It's good. If there's questions and that's.
Okay. Yes. Yes. Small part is independently.
It's like a miracle of nature.
Well, obviously,
I know, man. It's always looking like
full. It's unique.
We had a version of in 2006 and it was not like this.
Yeah.
It was way more complex.
Yeah, it's funny nowadays. You just see the CD drive in the laptop, and you know it's all.
This is done through what is called a generalized check. If I have time, I will talk about it. This is the framework where the exception is the framework
I just finished doing my work for summer. They should pay me. But the University of Amsterdam has now officially verified my diplomas. So if they check their mailbox, I don't see any reason why I should be finished the process. Obviously, it's.
And then you're ready to apply. So you're ready to apply.
I should be. Well, yeah, I mean, I put on hold sort of, some dependent on sample. So for example, like the legislation of the professional
Oh,
body.
right.
It's going to require sample. So there's a few things that together, but basically I should be ready with the new.
Oh, you got this?
Well, the University of Amsterdam, very.
Oh,
So, let's see how Sam is going to respond to that. Yeah, you- So, yeah.
okay, but I mean,
So they had like a very quick response time. So, one day.
but that you know from us. But whether Sacco will convert that to now summary almost here.
You don't have to have, it's not gonna happen.
Yeah, I'm going to go probably tomorrow. And that actually has worked. I mean, to just keep going and just walk. Yeah, yes, yeah.
It's next to Hatfield Station, where we're going to visit more of the Hatfield.
Oh,
I mean, I don't know, I'm not sure if they already tells you that much, detail.
no, I mean,
But that was useful when I was applying, we were just went there.
books.
I don't know how you say.
Yeah,
Yeah, take a look. Unfortunately, you're going to be hard going. You think you can try to.
Sorry?
Okay, let's continue with the third lecture by Jaco on the context.
Yeah, absolutely. Thank you, Kostas. So, what I want to do in the next two lectures is move towards quantum complexity. So, what we've been discussing in the last couple of lectures is chaos. We started with versions of classical chaos. What we saw there was this ergodicity in phase space of chaotic systems. And we motivated a couple of diagnostics for quantum systems, and this form factor harmonic correlating, and discussed what are the sort of signatures of chaos that one would look for in these diagnostic tools. And what I want to introduce today is the notion of quantum complexity, which has one of its utilities as a diagnostic of quantum chaos as well. And the basis that it is formed out to be a diagnostic of quantum chaos, which I will describe, is essentially based on ergodic behavior, but space, but in some Hilbert states. So the second that we have in mind for quantum complexity is, suppose that you have a quantum system, and at your disposal you have some set of operations. Let's say 1, 2, all the way on to say a unitary operations that you can act on states in the Hilbert space. And these are called the quantum gates in the complexity. So a lot of the nomenclature in quantum complexity is borrowed from quantum computing. So this is why gates is chosen. You can think of a circuit in some quantum computer, and these gates transform an input state in a particular way to produce some output. So this is the first thing that you will need. The second would be some target that you have in mind. So this is something that you want to generate through the action of unitary operations on some reference states. So it's the target state and the reference state. And the idea is that you can obtain this target state by acting with some sequence of these unitary operations. Equals to 1 of some, let's call it C prime, or unitary operation, with some permutation here. So, you know, when I is equal to 1, you could pick U5, for example, when J is 2, U3, and so on. So some particular combination of these unitaries on the reference state should give you the target state in this case. This is the sort of set that you have in mind. What we now want to do is have a notion of how hard is it to obtain this target state from this particular reference state. And that's how difficult that operation is known as quantum complexity from this particular reference state. And that's how difficult that operation is known as quantum complexity. So what we're going to need in order to do that is some appropriate notion of metric, some suitable metric on these unitaries to quantify how difficult it is. So one simple choice that you can make, for example, is to say, well, let's say that I'm simply going to sum up the number of unitaries. So it goes from 1 up to C prime. And each unitary has an associated difficulty, some weight associated with it. So some weight, this is one way you can think about the complexity. So say, for example, U1 will have order 1, U3 or 2 is a bit more harder to perform than 1. And what you will then do is minimize over the choices of these permutations. So suppose I can obtain this target state in several ways. We'll choose the least difficult option of those two, and that's defined as the complexity. So this is quantum complexity in a nutshell. This is one particular choice of a metric that we can make. And as I mentioned, complexity is conjectured to be a diagnostic for quantum chaos. systems. And how can we see that? I'm going to make a very heuristic argument for why that is the case. So the idea is the following. Let's just make a very simple choice for complexity in this case. Let's assign a weight of 1 to all the unitaries in this case. So let's say that in my example, this is just to illustrate the big idea. And the idea is that this argument should hold more generally. So let's say that we minimize over these possible choices of unitary operations that you can make. Summing where j is from 1 up to c prime of the weight of 1. So all of the unitaries are weighted the same, just for weight of 1. So in other words, the complexity is now given by how many unitary operations I've acted on with. So let's just write down the first few ones just to get the feel of what it is. So of course, let's try to organize the states in the Hilbert space relative to the reference state in terms of their complexity. So if complexity equals to 0, there's a single state, and that is sigma r. And there's a single state of complexity 0, no unitary gate is active on that state, so the complexity of 0. For complexity equals to 1, this metric, well, I can choose any one of the n unitary gates that I have at my disposal. I can act with them exactly once, so they are in states. That satisfies this. And each of the four uj acting on the reference state. Now, if I choose c is equal to 2, then of course I could have acted with one of the unitaries and then again any of the other n unitaries. And then I have n squared states in the subspace. And so on. Now, I should caution here immediately that what I am assuming is that all of the states that I'm generating this way are unique. In general, they will not be unique. You will often generate a target state multiple ways. But for the sake of this simple heuristic argument, let's just assume that they are unique states and the discounting goes through.
So, question. This all seems very basis dependent, in the sense that if I choose a different reference data, I get a different answer.
Absolutely.
So, is this a problem?
So it's this is something that that people are discussing and there doesn't seem to be an objective measure of complexity. It's dependent on firstly your choice of reference state and on your choice of unitary gates. With that, so the idea would be that what you want ultimately would be for, so you want a holographic description of complexity. So complexity is conjectured to be due to black hole theory of body for, so you want a holographic description of complexity. So complexity is conjectured to be due to black hole theory of volume. The idea would be, can you find the appropriate prescription for choosing the reference state and target state? This is still a question on how this should be done. So the amount of ambiguity you have here is unappealing, but the idea would be that there is some choice that you should make, hopefully with some physical underpinning to it that will give you that choice. But yes, certainly there's a lot of ambiguity in this construction. There's a lot of ambiguity. I will present as we go on notions of complexity. So certainly it's always going to depend on the unitary gates and the reference state. But there are notions of complexity that have more ambiguity than others. And others that have more physical underpinning, but there's always going to be some form of ambiguity in the description. Unfortunately, that is not something that one can get away from.
Yeah. Have there been any attempts to kind of maybe like average over reference states or?
That's one possibility that one could do. So average over reference states.
Or some way of kind of characterizing like the overall system by looking at a whole, by having a complexity which takes into account like a large number of reference states.
Yeah, I think in a way that have been practiced, but the other thing is also that what we're going to get to is the Nielsen description, where the important thing is not the absolute complexity of the state, but the relative complexity of the state. So you get from one state to another. So you should think of the reference state as being something that you're given. So the state in which the laboratory is prepared, and I want to end up in some final state. So the question then is the relative complexity. So I'm going to add some set of unitary operations to prepare a target state. In a different laboratory, we start from a different state, and have to prepare the target state. So what happened at level was the question?
No. So, one thing that I just want to confirm, as you just said, we can need to perform an average over states, right? When I say we are performing an average over all the states, and I don't think like it's a very desirable thing to do in terms of experiments, because then you need to prepare your state in like a supervision of all your other states, right? And then
That's true. So from a mathematical viewpoint, that's really different state. But say that you have something like a particular sample in which you don't know the impurities for the sample. You can still do the averaging over not the full Hilbert space, but sort of the Hilbert space of possible configurations of this crystal. That's a possibility. That's what I could do. If you don't have, if you don't have access to the precise configuration of it, then typically averaging is a good thing to do in that case. All right, so as I say, so this is how it's going to go on. If you have C at a particular value, it's always going to be in raised to the power of that number of states, roughly speaking, up to this double counting that number of states. So let's say that I have a large but finite dimensional Hilbert space in this case. So there's some number. So then, in other words, the C is going to have to terminate. At some point, you're going to count every single possible state in the Hilbert space. And then the total number of states is of course just given by a sum, where j runs from 0 to n of n to the j. So we actually of n, which is C max. It is C max into the C max plus 1 minus 1 over n minus 1. And of course, if n is greater than 1, C max is quite large, then we can approximate this by 1. And we can say that this is, of course, just into the C max plus 1 over n minus 1. And I want to figure out the ratio of states that are in the maximal complexity state relative to all others. I need to I need to divide this number here by into the C max, because there are into the C max states and C is equal to C max. So what's the ratio of states in that case? And of course you can just do it here, and I'm going to get n over n minus 1. So if you have a large number of unitary gates, this is telling you that the majority of states are going to be at the maximal complexity. And it gets very low populations as you go in low complexity. So the majority of states are sitting the maximal complexity, in space. And larger than again, it's almost all of them. All right, so this is just a very simple accounting argument here. And now the key point comes in the form of chaos. And if I have some chaotic order, so some different states, then I talk about it. I'm going to use it. It's on different states. If this is a chaotic Hamiltonian, then the idea would be that it explores this Hilbert space logically. So it's going to, at some point, be in a linear combination of only one of those two states. So if I have a chaotic system, what I would expect is that as a function of time, if I have the complexity of this state as a function of time, so this time evolved state, what I would expect is that it's going to grow linearly, and it's going to grow linearly over time because we've essentially said that there's no ambiguity in the counting twice linear. No? In general, this will be not a one that might slope slightly towards the top, but so the estimates made by Susskind and his collaborators are that this should be reached in exponential time, and this should be doubly exponential time. in a multi-coding system. Yeah, so I'm just essentially comparing the time scale here to the, I've only browsed a little bit because unfortunately it was not so. We had a bit with last night again. But it's double exponential in, if I recall correctly, maybe small mean over there. If I recall correctly, but I'm speaking of the direction, I'll have to post the reference. The point just being that this time scale here, is at maximum complexity, is the vast majority of the this chaotic automation. And this you should contrast with a system that's not chaotic, where the number of states that we're going to be exploring is going to be much smaller. So in a integrable system, for example, you can expect something like maybe it goes to B, it stays at maximum complexity for a short time, and then comes back to before the motion completes. So this is why complexity is thought of as a possible diagnostic for chaos. Of course, there are some details that we've sort of pushed aside, like the double counting possibility that we have. We have assumed that the chaotic Hamiltonian will be the chaotic in the Hilbert space. I think it is a reasonably safe assumption based on the fact that it's a chaotic phase space in the classical system. I think that's a safe assumption, but these are things that one should test rigorously. But this is the heuristic idea at least. Now, right. So this is as I said, why complexity is thought of as a diagnostic for quantum chaos. The idea would be that take some reference study, evolve at a time, and measure the complexity of that system. Here we've used a very simple metric for deciding the complexity, that is sum over 1 as the weight allocation. But I'm going to introduce a couple of metrics, and that's probably used in the future, and we can discuss it in detail.
Can I ask a practical question? Sure. How difficult is this to do? In the sense that if you have some state, say the vacuum with your other state, and you start acting on the state, how many titrations do you really do to measure the complexity of the state? It seems like it's maybe correct in principle, but in practice, what's Cmax for a generic system?
Yeah, it's a difficult computation that you don't do mesh. So, and certainly in this picture that you have in mind, we have a discrete set of gates. It's a very hard computation to do because the combinatorics of the gates that you act on, the order in which you act on the state, is a difficult one. The crutch that I'm going into is just now is that you think of the unitary gates belonging to some symmetry group. The symmetry groups here a lot more computational power at your disposal. Of course, the question to ask then is, well, how we're going to look at to a even physical system. That is still an ongoing problem. So how to treat derivative computation, for example, in this case, if the Hamiltonian is not from some certain symmetry group. But at this stage, the computations are done on the level of symmetry groups, where a lot of it is tractable, using things like given states, like kind of house code formulas, and so on. But in general, I would imagine this is quite a hard computation to do. Fortunately, system.
The classical analog of all this, so it's called Laurent complexity, which is purely classical in nature. It's essentially, the shortest program that prints a particular number is the Laurent complexity of that number. That it's really impossible to tell whether you don't know. So, for example, you take a number like pi expressed in strange base, and the program can convert to the space, and that's your number. In general, for most programs, they're just like a strange number. So it's a long program. So you would say that almost all numbers there are complex, just like you're saying almost all states or that. In principle, it's difficult to distinguish, right?
Absolutely, yeah. The examples that the people produce are
right.
absolutely, yeah. The examples that the people produce are just quite simple. let's say, is based primarily on non-sequitur arguments, which are substantially simpler than what you really want to do, which is this idea in a quantum computational setting where your dates at the street. Most states are complex. It's extremely hard to give you a generic set to tell how complex it really is. It's a very difficult ascertainment to do for that state. Because what you need to get a generic set to tell how complex it really is. It's a very difficult ascertainment to do for that state. Because what you need to do is, in order to determine how complex it is, you have to run the algorithm backwards, right? You have to say, well, in order to determine how complex it is, you have to run the algorithm backwards, right? You have to say, well, I give you this state, and now I need to disentangle that set of unitary back to the reference state. And doing that is, in general, really hard to do. Absolutely. Right. So, yeah, that's actually a great segue to what we're going to be doing. We're going to be simplifying the problem substantially in this case. And by simplification is to not think of the unitaries as discrete operations, but to have a continuous notion of complexity in this case. But this is the so-called Nielsen complexity. Nielsen. And the idea here is that instead of having a set of discrete gates interacting with the reference state, you choose your unitary to be from some symmetric. So you use the gene. Along with this, you make a choice of the reference state. And the set of accessible target states are all the ones where I act with some unitary from this group on the reference state. And this family of unitaries is, of course, going to depend on the specific group that you choose. And that group is going to be labeled by real numbers that exponentiate the algebra elements of this. So it's 1, it's 2, all the way up to this thing. So this is the general form we're going to get, and this target state is going to be represented as a function of these parameters. It's 1, it's 2, all the way to this thing. This is the set of possible target states that you can have. So this is the first two choices. All the way to this thing. This is the set of possible target states that you can have. So this is the first two choices. Yeah. So this is the first thing one needs to do. And what we now need to do on top of this is associate and measure how difficult it is to apply these unitaries on reference state. So we need a suitable metric. Now, the choice of metric is not unique.